We've now seen how the randomized controlled experiment confronts the fundamental problem of causal inference by constructing a counterfactual through the control group and making sure that the pretreatment variables in the control group are the same as those in the treatment group. We can then use the difference in average outcomes between the two groups to derive the average treatment effect, the average causal effect of the treatment on the outcomes. Now, the randomized controlled experiment is by far the cleanest way of identifying these average treatment effects. And for that reason, it's often called the gold standard of causal inference. The problem is that in economics and in many other social sciences, the data we primarily work with typically does not come from randomized controlled experiments. It comes from the real world. But we can still use the logic of the randomized controlled experiment to think about how we might approach such data. In particular, we can look in the data for what we call natural experiments. Natural experiments are experiments that aren't designed by researchers, but that simply happen because of the way the world works. Let me give you an example. Most charter schools have fewer spaces available than applicants to the charter schools. So how do charter schools determine which kids get into the charter schools and which kids don't? Well, it turns out that most charter schools are required to use lotteries to determine who from the applicant pool gets into the schools. So we're using a random process to decide which kids from the applicant pool end up being treated by the charter school and which end up not being treated, which end up becoming part of what we could consider a control group. And because the process of determining which kids end up in which group is random, we can be reasonably sure that the pretreatment variables are the same across the treatment and the control group, just as they are in a research-designed randomized controlled experiment. So in this case, the natural experiment emerges simply because of the way that charter schools run. And because what comes out looks a lot like a randomized controlled experiment, we can then derive the average treatment effect of the charter school on kids who've applied to the charter school on various outcomes. Outcomes like graduation rates, years of schooling, test scores, maybe even future wages. So here we have an example of a natural experiment that looks a lot like a randomized controlled experiment, and we can directly apply the lessons of the randomized controlled experiment to the natural experiment. But the experiments we see in the real world don't always have such clean randomized controlled selection into treatment and control groups. Think, for example, about the Head Start program. Head Start is a federally funded preschool program for disadvantaged children. And again, just like in the charter school case, there are fewer spots available in Head Start centers than qualified disadvantaged kids. So how do we choose who gets into the Head Start program? Unlike the charter schools, Head Start programs do not use lotteries to determine who gets in. Instead, the Head Start centers choose which disadvantaged kids get to come to the Head Start centers. And it turns out that most people who run Head Start centers would really like to make a difference in the world. And so the kids they end up choosing are the ones that are most disadvantaged among those who are qualified. So now we have non-random selection into the treatment of the Head Start program. We're not using lotteries. Instead, Head Start centers choose who gets in, and they choose the most disadvantaged kids. So let's see what that does to our experiment. In a typical randomized controlled experiment, if there's no difference in the average outcomes between the treatment and the control group, we would conclude that the treatment had no causal effect on the outcomes. But can we do the same in the Head Start experiment? If there's no difference in the average outcomes of the kids who are treated by the Head Start centers versus those who are not treated but qualified, is that evidence that the treatment had no effect on the kids in the Head Start centers? And the answer is no, because now because we have the most disadvantaged kids in the Head Start centers, we would expect, if the treatment didn't have an effect, for the average outcomes of those in the Head Start centers to be worse than those who aren't in the Head Start centers, because the Head Start centers admitted the most disadvantaged kids. If the average outcomes are actually the same as those for the kids who didn't get chosen, it's actually evidence that the treatment had a positive effect on those children. But we can no longer use the difference in average outcomes between the treatment group and the control group to derive the average treatment effect. We have to think of ways of adjusting for the fact that there was non-random selection into the treatment and control group, so that we can recover what the average treatment effect would have looked like had there been a truly randomized controlled experiment. Now, whenever something enters the experiment that causes something to not be constant between the treatment and the control group, we call that a confounder. So a confounder is anything that is not constant between the treatment and control group. And typically the way that the confounders enter the experiment is through the non-random selection into treatment and control groups. Let me give you another example. There's a documented strong negative correlation between education and smoking. In other words, the more education people get, the less likely they are to smoke. Now, for a long time, people have looked at that correlation and said, well, that's evidence that more education causes people to smoke less. And we can tell a plausible story. Perhaps people who get more education get more information, can make better decisions, and so they end up smoking less. But is that really what that correlation tells us? Does the data that forms the correlation come from a randomized controlled experiment? If it did, then the correlation would in fact be evidence of education causing less smoking. But it of course doesn't come from a randomized controlled experiment. The treatment here is education. Who gets more education, who is treated, and who gets less education and is not treated? Well, we're not randomly choosing some people to get more education and other people to get less education. The level of education that people get comes from the decisions that they make about how much education to get. So we have to ask, what is it that causes people to get more education? And of course, there are many factors that go into those decisions. But one of those factors is surely how much people think about the future when they make current decisions. The more someone thinks about the future as they make current decisions, the more likely they are to get more education, because they're thinking about the future benefit of higher wages and better jobs and more meaningful employment opportunities. And the less people think about the future as they make current decisions, the less likely they are to get more education, because they're not thinking about those future benefits. So how much a person thinks about the future as they make current decisions is a characteristic of a person. And that characteristic surely has something to do with how much the person smokes. If someone thinks a lot about the future as they make current decisions, then they're going to think about the future health consequences of smoking as they decide how much to smoke now. And so they're going to be less likely to smoke. If they think less about the future as they make current decisions, they're less likely to think about those future consequences and more likely to smoke. So the very characteristic, the very pre-treatment variable that causes people to get more education is also causing them to smoke less. And if that's what's going on, we would see a correlation between more education and less smoking. But that correlation would have no causal explanation. It wouldn't be that more education caused people to get less smoking. It's that the underlying characteristic that caused them to get more education is also causing them to smoke less. So a mere correlation that we observe in real-world data does not imply causation. It doesn't imply causation unless the data comes from a randomized controlled experiment or something that has the features of a randomized controlled experiment. So when we think about what the experiments in the real world lack that a randomized controlled experiment has, we have to confront the issue of confounders. And confounders enter the analysis through the selection into the treatment and control group. That selection has a lot to do with the incentives that people face in the real world. In the Head Start example, the people who ran the Head Start centers and wanted to make a difference had an incentive to admit the most disadvantaged kids into the program. In the smoking example, the people who think more about the future had an incentive to select into more education, but that very characteristic also causes people to smoke less. So the selection into treatment and control in the real world often confronts the incentives that people face in the real world. And that's what produces these confounders. So it's natural that causal inference and thinking about confounders is an area that emerged within economics, because economists are typically very good about thinking of incentives. And the branch of economics that emerged to deal with how can we adjust for the presence of confounders in real-world data so that we can recover what the average treatment effects would have been in a randomized controlled experiment. That branch of economics is called econometrics.